Okay, this is for Tuesday, August 16th, Math 1325. We're going to spend 2 days going over the review for the final, doing 1 through 15 today and 16 through 30 tomorrow, which will be the last video day of the semester, and then you'll have a 2-day window to take the final one time, either on Thursday or Friday. So whenever you think you're ready for it, you can take it, but if you want more time to study and practice and complete everything, you got all the way till Friday night if need be. And before we do the review, I want to go back to that problem number 5 in the last homework 7.5. I looked at what I did. It sometimes helps us to back away for a second and look at it with a fresh view the next day. And it was just one little tiny mistake I made. And it's kind of like when if you're writing a paper for an English class, if you have a misspelling, you normally don't notice your own misspelling, but what I did is I did a completely new problem and then I saw what I was doing wrong. So let's just do that problem again. So we know the answer is supposed to be 37 over 12. We have the area between these two curves, the cubic function and the quadratic function. So the cubic function is x cubed minus x squared plus x plus 1. And the quadratic, oh no, I'm thinking of the wrong problem, plus x plus 3, okay. 4x squared, 4x squared minus 5x plus 3. So when do these functions equal each other is the first question always. We need to find when they equal each other because that's the spots where we might have to break the integral into separate parts. If one curve is always above the other one, then, and they maybe don't equal each other, or maybe they equal each other twice and one curve's always above the other one, then you can just do an integral for the whole part of where it's shaded. So the 3's do cancel out here. You could subtract 3 from both sides. I'm going to get the left side to have all the stuff and then make the right side equal 0. So minus this 4x squared over here. Negative x squared minus another 4x squared would be negative 5x squared. Add this 5x over x plus 5x is 6x. So then factor out an x. And then this factors into x minus 2 and x minus 3. So there's 3 times these functions equal each other: 0 itself, positive 2, and positive 3. If you set all those equal to 0. 0, 2, and 3. So what's happening is there's a quadratic parabola like so. And then there's a cubic function, and it comes up right at 0, right at the origin. They cross, and then they cross again at 2, and then again at 3, because the cubic function rises faster. That's not the perfect drawing, but there is 2 shaded areas. There's this one, and there's that one. And then in the rest of the time, there's nothing else bounded. This is all unbounded over here. This will eventually separate farther as you go higher up. This area is unbounded. There's just these 2 areas that you could shade in, this and this. And there's a reversal, though the cubic function's above the quadratic from 0 to 2, but then from 2 to 3, the quadratic's above the cubic. So that's why we do need 2 integrals. We need an integral from 0 to 2, where the cubic function, x cubed minus x squared plus x plus 3, the cubic function is above the quadratic. 4x squared minus 5x plus 3. So that's the first integral we're going to figure out. And then we're going to add to it from 2 to 3, these things reverse each other. So this one's first minus that one. because then the quadratic function is above the cubic function from 2 to 3. So when you put this first one together, you got your x cubed. There's going to be a minus 4x squared right there, along with this negative x squared. That's negative 5x squared. You got your x, and then this double negative will turn that into positive 5x. Plus 1x is 6x. And the 3 minus 3 cancels out. In fact, this part right here is the same as when they equaled each other. Right here, x cubed minus 5x squared plus 6x. And then it turns out when you reverse it, and you can do it slower if you have to, put this one first and that one second, distribute the negative, combine like terms. But it turns out if you're doing the same function and it's just switching places, like here, the cubic was above, now the cubic is below, the quadratic was below, now the quadratic's above. It's the same two functions. So it just reverses everything, and you get negative x cubed plus 5x squared minus 6x on the second half. So that does save a little time to know that it just switches signs like that. So the integral, the antiderivative of x to the third is x to the fourth over 4. Increase the exponent by 1, divide by the new exponent. And then same thing here, minus, increase the exponent by 1 and divide by that exponent. Increase the exponent by 1 and divide by that exponent. And you can even reduce this to 3. From 0 to 2. So we need big F of 2 minus big F of 0. And I did this part correct. 2 to the fourth is 16. 16 divided by 4 is 4. 2 to the third's 8. Times 5 is 40, but 40 doesn't divide by 3. And then 3x squared. 2 squared is 4, times 3 is 12. So this is 12 plus 4, 16 over 1, minus 40 over 3. And you can change this to 48 over 3. 48 over 3 is equal to 16. Minus 40 over 3 is 8 over 3. This first part is 8 over 3. You're technically doing f of minus f of 0, but that is 0. Because this would be 0, this would be 0, this would be 0. So it helps to have f of 0 there, because otherwise we'd have to calculate that and subtract it. So that part was correct. What I did wrong was next, the antiderivative will be the same thing over here except opposite signs. So you'll have a negative for the x to the fourth. You'll have a plus for the x to the third part, and then you'll have a minus for the 3x squared. From 2 to 3. So now you have to do big F of 3 minus big F of 2. And the mistake I made was I assumed that the F of 2 was the same, and it's not. And I'll show you why. So it's better if you just calculate things instead of just assuming what's going to happen. I was trying to take a shortcut, and it cost me from figuring out what was going wrong. So big F of 3, we would put 3 to the fourth, that's 81. So that is negative, let me put a parenthesis here because there's going to be two parts. Negative 81 over 4. And then 3 cubed is 27, but divided by 3 is 9, times 5 is 45. And then 9 times 3 is 27. That part is big F of 3. And then minus big F of 2. Now, big F of 2 is not the same as this big F of 2. I thought it was, and I just put 8/3 here. That's what was wrong. But the signs are all opposite, so that's not true that it's the same. So 2 to the fourth is 16. Divided by 4 is 4, but it's negative 4, not positive 4. And then you'll get 8 times 5, 40 over 3, but it's positive, not negative. And then you'll get your 2 squared is 4 times 3 is negative 12, not positive 12. So it turns out this is negative 8 over 3, not positive 8 over 3. That's what I was doing wrong. missing this double negative is why I was getting a negative answer. Everything else I was doing right, but it was, once you get flustered in the middle of a mistake, you can't sometimes see your mistake till you step away and let it sit for a little while. So this was 18. This part here is 18. And if I have a, let's see where I can put it, negative 81 over 4 plus an 18 over 1, and then you have to multiply 18 by 4, which is 72 over 4. So that part's negative 9 over 4. Negative 9 over 4. So what we actually have is 8 over 3 minus 9 over 4, but then plus 8 over 3. 8 over 3 minus 9 over 4, but then plus. Now, see, I was putting a minus right there. It was the only mistake. One little sign error can throw the whole thing off, and then it's really hard to find your mistake sometimes. So we're going to multiply this one by 4 over 4 to make it over 12. That's 32. And of course, this one's the same thing, positive, but I was canceling them out last time. And then multiply this one by 3 over 3. So 32 plus 32 is 64 minus 27 all over 12. And that's 37. 37 over 12. That was it. So just that one little sign mistake right here. I was assuming it was just minus 8 over 3, but it was actually minus negative 8 over 3. So that settles that one, at least. That's how number 5 should have gone yesterday. Okay, now on to the review for the final. Okay, so we got that situated, save that, and here we go, 30 problems. And again, you can do this more than once. It's treated like a practice test, so you don't get all the help you get during a homework assignment. There's no help me solve this, view an example, ask my instructor. You don't get to put answers in and check them. This is like a practice test, so you do it all one sitting, hopefully. You don't have to do it all in one sitting, but the idea is one time you should practice for the final by doing this all in one sitting. Treat it as a practice run of the test. It's very often I get students that their test scores end up very close to their review scores. And obviously this can happen to anybody. You can run out of time or be busy with other things and just don't have the time you wish you had to put into this. But somebody will get a 43 on the review and they get a 45 on the test, and then maybe they're wondering why they did so poorly on the test. Or they get a 90 on the review and a 90 on the test. That happens very often where the test scores are real close to the review scores. So we have a linear function, 5x plus 8, and we want to go through this stuff that eventually becomes the derivative definition once you add the limit idea to it. But this part of it was taught in algebra. This is called the difference quotient, although they're having me slowly build up to it here. So the function is 5x plus 8. And first they want you to do f of x plus h. That's part A. So you literally just stick an x plus h right there where that x is. So 5x plus 5h plus 8. Then the second thing after you get f of x plus h is you minus the original f of x. And when you do that, all the parts of the second half cancel with stuff from the first half. So I've got my 5x plus 5h plus 8 from that part. And then we're going to do minus this, which switches them. The 5x will switch to minus 5x. The 8 will switch to negative 8. There's two terms there. They should both cancel, whether you have one term, two terms, three terms, however many you have in the second half, the f of x. They should always cancel stuff from the first half. And in this case, literally all that's left is 5h. And then you can divide by h, 5h over h. The third step is you divide all this by h. And what's causing the issue in the derivative definition is that we're trying to do the limit as h approaches 0, which in a rational function means hoping to plug 0 in, but you can't plug 0 into a denominator if it's going to make the denominator equal 0. So that's the whole issue, is this h in the denominator causes all the issues until you get all this to cancel. Then some way or another the h's will end up canceling, but they don't cancel until that point. So then in this case, all we're left with is 5. And this should make sense now that you know more about derivatives. If your original function is 5x plus 8, that's linear. The derivative of that is the slope 5. And that's what this is saying, is that the derivative is 5. If I did, we're not doing the derivative here, but now that we have that knowledge, we can use that to help us. Okay, now it says without using your calculator, but during an exam, nobody's going to know if you used your calculator. But the point of this was, do you know what these changes do to a function? Because it does the same to any kind of function, whether you have x squared quadratic, or you do an x cubed, or a square root of x, or an absolute value of x, any of the basic parent functions. There's a change with x. So this x plus 5, you might think plus 5 for an x is to the right, but that's actually opposite, and you go to the left 5. And then the number that's not with x affects y, and that you do that one like it looks, so it's up 2. We want to take the basic parent function for quadratic, this one, and we want to move it left 5 and up 2, like so. Not just left 5, and not right 5 and up 2, but left 5 and up 2. So probably B is the most tricky wrong answer there. That's the more logical answer, but they end up doing the opposite for the left and right. Okay, vertical and horizontal asymptotes for rational functions. We got a 3 minus 4x over 4x plus 16. Anything that makes the denominator 0 is definitely not part of the domain. Most of those values are vertical asymptotes in a rational function. The only way they wouldn't be is if you can factor the top or bottom or both and then cancel anything. So the bottom actually factors into 4 times x plus 4, but the top doesn't factor, so nothing cancels. If anything cancels, then stuff that would have been making the denominator 0 is a hole in the graph instead of a vertical asymptote. And it still would not be part of the domain, but it would make the graph look different. So we always want to check, can we reduce this fraction before we do anything else? We can't. So anything that makes the bottom 0 is a vertical asymptote then. And this has one x value that makes the bottom 0 because that's linear, 4x plus 16. And maybe you can see it right here that it would be what makes this expression become 0. So divide by 4, x equals negative 3. This is the one and only vertical asymptote for this problem. A problem can have none or a bunch of them. So there's no vertical asymptote, or there's one, or there's a bunch of them. But type an integer or a fraction, but this is an equation, x equals negative 4. A vertical asymptote is always x equals something, because it's a vertical, imaginary vertical line. So sometimes they don't put the x equals, and then students forget to put it themselves. Horizontal asymptote, there's 3 cases. Case 1, if the degree in the top is bigger, if the degree in the top of the fraction is bigger, then there is no y horizontal asymptote. You just put none or click the option that there is none. If the degree in the bottom is bigger, then there's an automatic y equals 0, the x-axis. And then finally, this is the case we have, although you might get tricked here if you don't look at this properly. The degree of the bottom is 1. If somebody just looks here, they can miss this problem. The degree of the top is 1 because they have the top out of order. So you might have thought the degree of the bottom was bigger and the answer was y equals 0, but that's because they put this out of order. If you don't want to get tricked by that, write it this way. And that will also help not only in identifying which case we have, but also what the answer is going to be now. Because if the degree is equal in both top and bottom, like we have a 1 in the top, we have a 1 in the bottom, we have equal degrees. If the degree is equal, then you do the two leading coefficients divided by each other, the ratio of the two leading coefficients, which is actually -4 divided by 4, not 3 divided by 4, which could trick somebody. So somebody might say y equals 3/4 and get this wrong, but it's actually y equals -4/4 or -1. So it has 1 horizontal asymptote. It can only have 1. It would never have more than 1 horizontal. There's either 1 or none. The vertical, there can be multiple ones of that, or none. So then the idea on the graph is if you just look at these asymptotes, you can eliminate some of the graphs. -4 for x and -1 for y. So this graph's definitely wrong because the the horizontal asymptote's above the x-axis. It should be below it. This one looks like it's right on the x-axis. This one seems to be a little above, so right there, a little bit below. And this certainly could be -4 over here since these are going by apparently 5s, 5, 10, 15, 20. So it looks like D is definitely correct. It's got the -4 vertical asymptote and apparently -1 for the y. It's hard to tell because it's so close to the x-axis. But that definitely could be the answer. C is definitely wrong because the horizontal's above the x-axis. And same on A, it's way above it. And then here it looks like it's right on top of it. But even if it wasn't, the x equals -4 is definitely wrong. They got this both on the axes. So this one's definitely D. Okay, next up is solving exponential equations. One type is where you can make both the bases the same. Another type is where you have to use logs when you can't make both of the bases the same. But these two I can make the same. Sometimes you can make the bigger one look like the smaller one. Other times you have to change them both to a smaller one. So if there was a way to make 64 look like a 16, but 16 to the first is 16, and 16 squared is 256, which already bypassed 64. So that means I can't make the bigger one look like the smaller one. Maybe I can make them both go to a smaller base, like say 4, because 4 to the first is 4. 4 squared is 16, and 4 cubed is 64. They can both become base 4. So in place of the 16, you put 4 squared, and the other exponent's still there. And in place of the 64, 4 cubed, other exponent's still there. Then rules of exponents, if you have x to the m times x to the n, that's when you add the exponents. But if you have x to the m to the n, where there's one base and a double exponent, there should be times right here. One base and a double exponent, that's when you multiply exponents. you never do exponents like they look. If you're multiplying, you don't multiply. If it looks like an exponent, you don't do an exponent. So this is not 2 to the x plus 3. This is just multiply them. 2x plus 6 using the distributive property. 6x minus 9. And now, because the bases are the same in an equation, the only way two powers can equal each other when the bases equal each other is if the exponents also equal each other. So in essence, the bases cancel out and you can set the exponents equal to each other. And both of these are linear pieces, so there's going to be one x value that makes these equal to each other. Minus 2x. And add 9. So 4x equals 15. And they'll do this on purpose sometimes, make it not come out evenly, just because they don't want somebody just plugging in like 1, 2, 3 and trying to guess to see if it works. So then you actually have to know how to solve it. X equals 15 over 4. Nobody would ever guess 15 over 4. And they already have the x equals, so 15 over 4. Type an integer or an improper fraction. So they want 15 over 4. They don't want a decimal. They don't want a mixed fraction. So especially on doing your tests in MyMathLab, you always have to read the blue part to see how they want the answer. Because if they want 15 over 4 and you put 3.75, even though that's exactly equal to it, they don't give any credit for that. Okay, that was an exponential equation. Now we're going to solve a log equation. In a log equation, the unknown can be in any of the three slots. Here they have log base x. That's the unknown. Of 625 equals -4. But the x could be in any of those three slots. It could be here, here, or there. And no matter where the x is, you still do this the same way. You got your three parts of a log. There's an equivalent exponential version. So you say to yourself, which of these three things is a base? And we read this log base x, so x is the base. Which of these three things is an exponent? A log is an exponent, so the -4 is the exponent. And then I haven't used the 625 yet. So this, we just went from log form to exponential form. They're two equivalent forms. Exponentials are usually a little easier to solve because we're more used to them from previous math classes. And now I just got to solve for x. So we've got a -4 exponent. I could make that 1 over x to the +4. And then the trick when you have a situation like this often happens in geometry. It even happens in trigonometry a lot. You interchange these two with each other. You can interchange two diagonals in a proportion. And then I can get rid of the fourth power with a fourth root. Then you got x by itself. And then when you have a radical of a fraction, you try to do each half individually. So I try to do the fourth root of 1 and the fourth root of 625. Any root of 1 is 1, so the top's definitely 1. And then you might not know that that's 5, but if you had a calculator that has the capability to do a fourth root, and here you can press the number 4, then you hit the math button, and there's a built-in cube root right there, but you can also do an x root if you want something higher than 3, although you have to type that 4 first to tell it fourth root. And it's a little strange because it looks like 4 times some kind of root, but it knows to put the 4 in the x slot. It just doesn't show it on the screen. So this will say 5 because 5 to the fourth power is 625. So that's what a fourth root means, is what times itself 4 times equals that. 5 times itself 4 times equals 625. And then because it's in the denominator, the answer is 1 over 5. Okay, use properties of limits to find the limit. So in a rational function limit, you can normally, in polynomials or rational functions, if you're doing the limit as x approaches 2, the first thing you try to do is plug the 2 in. F of 2 will often produce an answer. It will always produce the answer in a polynomial, and it will produce the answer in a rational function as long as it's not something that makes the denominator equal to 0. Although here it does. So I would try that first, plug 2 in and see what happens, but 2 squared is 4, 4 minus 4 is 0. So then you can do other things like there's the table method where you try to get real close to 2, like 1.99999 and 2.0001. There's the graphing method, but this was meant for algebraic simplification. The denominator is a difference of squares, x plus 2 and x minus 2. The numerator is a trinomial that might factor into x times x. If there's a negative in the back, you get one positive and one negative. Got to multiply to 12. 1 and 12, 2 and 6, 3 and 4, and it needs to subtract a positive 4. So that would be positive 6 and negative 2. So this is where I can factor and cancel. If I was graphing this rational function, it would only have one vertical asymptote instead of 2. The x plus 2 would still lead to a vertical asymptote of negative 2. And then the x minus 2, where if you solve that for 0, x would equal 2, that instead of being an asymptote, that would just be a hole in the graph at that point. So that's why you have to factor and cancel if you're looking for asymptotes. But here we're just doing the limit. So the issue was plugging 2 in right there was causing the denominator to be 0. But now I get a reduced version of the fraction. And in the reduced version, plugging 2 in doesn't make the denominator 0 anymore. So then it's like I'm doing g of 2, if you want to call it a different name, because it's not really the original f. F of 2 was undefined, but g of 2 is not undefined, and g of 2 is a simplified equivalent version. So that's the rule for rational functions, is if you can find the limit for this simplified version, it'll equal the limit of the full version too. So now I can just plug 2 in. 2 plus 6 over 2 plus 2. 8 over 4 is 2. And it's just a coincidence that we're getting 2 for a lot of answers here, but the limit would equal 2. If we did the graphing method or the table method, all the answers would get really close to 2. Okay, then the next concept in that chapter, the initial calculus chapter, is about limits. So you got your 3 major topics in calculus: limits, derivatives, and antiderivatives or integrals. So the next concept is, when is something discontinuous? Polynomials are continuous everywhere. Rational functions are continuous everywhere except for zeros of the denominator. Whether they're asymptotes or whether they're holes in the graph doesn't matter. Anything that's an asymptote or a hole in the graph for a rational function, vertical asymptote or hole in the graph, that's going to make it discontinuous. Now these would both be vertical asymptotes, but even if you get a hole in the graph, you would have to pick your pencil up and keep going around that hole, so that would be discontinuous. So 0 and 2 make these two denominator parts 0. The zeros of the denominator are 0 and 2. So the graph is continuous everywhere except those 2 places. It's at 2 values. And then, okay, so they're not going to let us just put in the 2 answers. It's one of these 3. So then it might help to see the graph of this, or use the table or graphing method. So we've got 7 plus x and x times x minus 2. So we have 2 vertical asymptotes. One is 0 itself. The other one is 2. The degree of the bottom would actually be x squared, would be 2. The degree of the bottom's x squared, the degree of the top's 1, the bottom's bigger, so y equals 0 is the automatic horizontal asymptote. Okay, and then if I was going to plug in 0 because that's the easiest one, but that one's taken already. So if we plug in 1, the top would be 8, and the bottom would be -1. So 8 over -1 is -8, so we're down here at 1. And then you could try plugging some other spots in. If I plug in 3, the top would be 10, the bottom would be 3, so that's 10 over 3. If I plug in -1, the top would be 6, the bottom would be -3 times -1, +3, so that would be 2. So typically with these graphs where there's 2 vertical asymptotes, you get one that goes like so, and then this one's going to go like that. And the one in the middle often will either be looking like a parabola, or sometimes it looks like a a cubic if it goes up. But this is probably what the graph looks like. So the limit as x approaches 0, on the left side it's going up to infinity, and on the right side it's going down to -infinity. So that's where the limit doesn't exist. It doesn't even equal. Sometimes if they both go up to infinity, they'll say that the limit is infinity, even though that technically still doesn't exist. But we don't even have an agreement on the infinities here, on this side or on that side. So the limits really do not exist. They do not exist, and they're not infinity or -infinity. You could, if they were both infinity or both -infinity on either side, then you could say that just to be a little more specific about it. So we have 2 of them, 0 and 2. Oops. There's 2 discontinuous spots, 0 and 2. The limit for the smaller, no, I'm putting this in the wrong spot. Yeah, it's here. 0 and 2. The limit for both values do not exist, and they're not infinity or -infinity. So if like on the one side, if both graphs went up, then you could say the limit at, there's 2 of them, 0 and 2, and then the limit for the smaller value could be +infinity. And for the larger one, it could be -infinity if they both went in the same direction. So if you would have had some kind of graph that looked like you had 2 vertical asymptotes, if you would come up like this and then go like this, sometimes the middle portion looks like this. It's okay to cross over a horizontal asymptote. And then maybe this one goes like that. So if these are both going up to infinity, then technically the limit doesn't exist still, but then you can be a little more specific and say the limit's infinity, because they agree that they're both infinity. And then here they agree that they're both -infinity. So it's still that the limit doesn't exist technically, but we can say that both sides agree to infinity or -infinity. Here, not only does it not exist, they don't even agree. The one side's infinity, the other side's -infinity. That was number 7. Okay, so this was a little complicated because there were so many options to pick from. Average rate of change. Average rate of change is starting to get you close to the idea of a derivative, but average rate of change is synonymous with slope. And it's really the slope of a secant line, not the slope of a tangent line. Slope of a tangent line is derivative. Slope of a secant line is just slope, like in algebra. So algebra would say that the slope is y2 minus y1 over x2 minus x1. In calculus, they just do it a little more fancy. They say f of x2 minus f of x1, and those are the same thing as y's, over x2 minus x1. So my f of x is 7x cubed plus 7. Part A, we want to go between 5 and 7. So the slope is f of 7 minus f of 5 over 7 minus 5, which is obviously 2 for the denominator. F of 7 would be 7 times 7 cubed plus 7. A lot of 7s there. Should have went to Vegas for 777. 2408. And then I can redo it with a 5 for the cubed part. 7 times 5 cubed plus 7 is 882. 2408 minus 882, and then divide by 2. The first one's 763. So this is such a cubic function, is such a fast rising graph when you get past the origin. And when you get to 5 and 7, the graph's like completely off the screen in 2000s and 800s. So the line, if you actually drew this out on a graph, the line would be almost vertical at that point to have a slope of 763. The slope is 763 between 5 and 7. Now when I do it close to this, it'll be much flatter. If I repeat this for part B, -1 to 1, and now we're not even going to need a calculator. So now the slope would be f of 1 minus f of -1 over 1 minus -1. So the denominator is still 2 by coincidence. Doesn't have to always be 2, but f of 1 is easy. You put a 1 right here. That equals 1 times 7 is 7, so 7 plus 7 is 14. But when I plug in -1, -1 cubed is -1 times 7 is -7 plus 7 is 0. So that's 14 divided by 2 or 7. And not only is this a cubic function, it's got a vertical stretching times 7. It already goes up fast, and then there's a vertical stretching. So what these two answers are saying is you have a shift up 7, and then you have a quadratic that's vertically, or not quadratic, cubic that's vertically stretched by 7. So from -1 to +1, the slope of the secant line that would go through the curve, it's not touching it once, it's going through it, this slope would be 7. But if I continued this all the way up to 5 and 7, it would take you a long time to get over to 5 and 7. The line would be virtually vertical way up there. Not quite vertical, but the slope would be 700 and whatever. So that's going to look like it's, to the naked eye, that would look, whoops, almost vertical. Okay, next what they want you to do is use the definition of a derivative. That's the limit as h approaches 0 of the difference quotient. F of x plus h minus f of x all over h. But when you're taking a test, they're not going to know how you did it. And at this point, you already know all the rules of derivatives, the shortcut rules. So for number 9, you could save yourself a lot of time if you just use the power rule. Since they gave me a polynomial, -x squared plus 7x minus 7. So the derivative, we now know from further chapters that this would just be -2x to the first plus 7. Instead of going through the whole limit as h approaches 0, f of x plus h, f of x plus h minus f of x all over h. And that's what problem number 1 was getting at too, is doing this is the main body of the derivative definition. Once you add the limit to it, then you have derivatives. But you can go through all this if you want, but the shortcut would be much easier here. So there's the derivative, -2x plus 7. Now plug 1 into that. Negative 2 plus 7 is 5. Plug 2 in. Negative 2 times 2 is negative 4, plus 7 is 3. Plug 3 in. Negative 2 times 3 is negative 6, plus 7 is 1. The graph is getting less and less steep. And that's what happens on when you have a upside down quadratic. You're getting first a positive 5 slope, then a positive 3. Now we're at a positive 1. If we kept going, it would be 0, and then it would turn around and be negative after a while. And that's exactly the idea of a derivative, is it's a slope of a tangent line. The slope's going from 5 to 3 to 1, getting less and less steep as you go around that upside down parabola. Okay, same deal here. I can just use the power rule. See, 9 was in chapter 2 and then 10's in chapter 3. So first they make you learn the definition of a derivative the long way with the limit as h approaches 0 of the difference quotient. Then you move to the next chapter and they say, oh, by the way, there's a nice little shortcut for doing this now that you see how it works. Minus x squared over 40 plus 12x plus 1. And you can even think of this part right here as negative 1/40th x squared. And it'll be easier to do the power rule. So y prime or dy over dx, derivative of y with respect to x, that's actually been going on the whole time. You just didn't tell you back then, because the derivative of y is just 1 times dy over dx, but that's just dy over dx. So the derivative of x cubed is 3x squared. Then here you would do 2 times negative 1/40th, which would be negative 2/40ths, or negative 1/20th if you reduce. X to the first power. The derivative of 12x is 12, and the derivative of 1 is nothing. So that's just straight power rule right there to review that. 3x squared minus 1/20th x plus 12. 3x squared minus 1/20th x plus 12. Okay, another rule is the quotient rule we learned early on in that chapter. I have two different functions of x divided by each other, so I got to use the quotient rule. 9x minus 1 over 2x plus 3. So the quotient rule is second function times the derivative of the first, which would be 9 since it's linear, minus the first function times the derivative of the second, that's linear, so that's just 2, all over the second squared. Now, in some of the homework problems, we just put this in and they took the answer. That's fine most of the time, but there is a slight danger that we might be able to get a 2x plus 3 factor in the numerator somehow. So if you can get a 2x plus 3, then you have to factor it out and cancel, and the bottom could drop to a first power. There's no way to know that without simplifying the top and putting the like terms together. So just to be safe, I'm going to go ahead and simplify the top. 18x plus 27. And then this would be 18x, but negative 18x. And this negative 2 would turn into a positive 2. Here we get lucky and the 18x's cancel. So 29 over 2x plus 3 squared. So if the top had had some x's in it, then we might have been able to factor out a 2x plus 3 in theory. Usually it doesn't happen, but if it does happen, then in a rare case, you would have to factor that. If you somehow ended up with 29 times 2x plus 3, for example, just making that up, but if that would have been what the top was, then you would have to reduce. They would count it wrong if you didn't. If you got this, you would have to do this, cancels one of these two, and this would end up being the answer. And you can't tell that from here. There's no way to know that from this mess. So 95% of the time it doesn't happen. But there are some rare cases I've seen where it does happen. I think we even had one in the homework where it happened. And if it does happen, you have to reduce. But usually it doesn't. And when it doesn't, then you could leave it in a big mess like this. But unfortunately, you wouldn't know that until you looked at it. So once I simplified it and it didn't happen, I may as well leave the answer in the simplified version because that looks nicer. So 29 over 2x plus 3 squared. Usually the denominator squared just ends up all the way to the answer, 95% of the time in quotient rules. Okay, now this one is not a power rule. There is one coming up that is right here. Because there's a negative 4x times the natural log of 4x plus 3. There's an x times an x going on. But on number 12, there's no 49t. You would need a t right here for this to be a power rule. I mean a product rule. This is the quotient rule. I mean not the quotient. This is the chain rule because the inside stuff is not just a variable. There's stuff inside of stuff. So they're reviewing some of these rules a little out of order from how we learned them, but that's okay. S of t is 49 times 9t cubed minus 5 to the 6/5 power. So if you just had 49t to the 6/5 power, that's what it looks like if you like zoomed way out. If you backed way up and you couldn't see the inside stuff clearly. If this was just kind of blurry, there's something there, it would be 49 times something to the 6/5 power. This is the power rule right here, where you do 49 times the exponent, base stays the same, and you decrease the exponent by 1. That's how the power rule works. So you do that first here. 49 times 6/5. Base stays the same at first. Decrease the exponent by 1. 6/5 minus 5/5 is 1/5. But then the chain rule is if you don't have just a t right here, if you just have a t, then this is all you do. Because really what you're doing is their chain rule is you're multiplying by 1. The derivative of t is just 1. But if this stuff's derivative is not just 1, then you got to chain it on to the end of the answer. So the derivative of this is 27t squared. And then the derivative of 5 is nothing. Let's see, 5 does not go into 6, it doesn't go into 49, it doesn't go into 27. So we're just going to be left with an over 5 in front. I can multiply 49 times 6 times the 27. So the numerator will be, wow, 7938, pretty big. And that took care of the 49, the 6/5, and the 27. We can put the t squared next if we want. Usually if there's a parenthesis with an exponent, we usually put that last. You don't have to, but it just is more convention to do that. So that's all you can do. You would not want to distribute this t squared in because the exponent would stop you from doing it. That would only work if there was a 1 exponent. So you could put this in the back or even the t squared in the top of the fraction, but there's different ways to write this in the end, but this would be the most normal convention to do, is put your constant in front, 7938 over 5. If you have a single term like t squared, you just put that next, because if there was no parenthesis, that would be all you would have. And then your 9t, t cubed minus 5, since the exponent decreased to a 1/5, there's no way to simplify anything. And we just put that in the back to get the messiest part in the back. Okay, the next two are two other rules. We've seen the power rule, we've seen the quotient rule, and now here's the chain rule. There's also the product rule, which we're going to see soon, but the last two rules were exponentials and logs. So 2e to the 3x squared minus 4. The derivative of an exponential, especially if the base is e, is, well, first for any base, the derivative of an exponential is at first itself. Then if it's not e for a base, you have to multiply by ln of whatever the base is. So if I was doing like 5 to the 3x squared, then I would have to multiply by an ln of 5. I am multiplying by ln of e here, but we should know from algebra that ln of e equals 1, so that doesn't matter. And then if the exponent is not just x, then the chain rule applies and you multiply by the derivative of the exponent, which would be 6x. And just like the previous problem, I can put the most complicated part in the back. And the 6x times 2 could make 12x. 12x, and then I would have e to the original exponent, because that always stays the same in a derivative or an antiderivative. So the rule's pretty short. You just, at first you write it down exactly as it is. It always stays the same first. Then there's a times ln of the base, and if it's ln of e, it goes away. And then you multiply by the chain rule if it's something other than just x. So 12x, and then we get the original e to the 3x squared minus 4. That's the exponential rule. The log rule is you do, especially if it's natural log, you do 1 over the stuff. And then there can also be a 1 over ln of the base. And then that's the opposite of the exponential. Instead of times the ln of the base, it's divided by ln of the base. And then chain rule, if the derivative of the inside stuff is something other than 1, then that gets multiplied in. That's the natural log or log rule. But we have a product rule to worry about first. And then in the middle of the product rule, at one point, we'll hit a derivative of that log. So on the review, there wasn't a product rule problem to review it because they knew you were going to review it while you were doing this problem. Negative 4x times ln of 4x plus 3. So unlike two problems ago where I just had a 49 in the front, that was a constant, this is not just a constant. This is 4x times another, we got two functions of x multiplied together. So we got to use the product rule since we have two things multiplied together that both have x. Product rule is first times the derivative of the second. So here comes the log rule. First you do 1 over the stuff. If it was anything but ln, you would have 1 over ln of your base of your log. So say it was log base 5, then you'd have 1 over ln of 5. But if anytime it's e or ln, then that's nice because that just goes away. And then you have to multiply by the derivative of the stuff inside the parenthesis, which would just be a 4. So this whole part right here, that's first times derivative of the second plus second times derivative of the first. And that would just be negative 4 since it's a linear piece. And the product rule does not have a divided by, that's the quotient rule. So I can put this times 4 with this negative 4x. That would make negative 16x over 4x plus 3. And nothing reduces there because of the plus. So you're just kind of stuck with that. Plus, or I can actually put minus minus 4, slide that in front of the ln. And I'm assuming we don't need to get a common denominator here, so let's put it in that way. And let's see, negative 16x over the 4x plus 3 minus 4 ln of the 4x plus 3. Negative 16x over 4x plus 3 minus 4 ln of 4x plus 3. Okay, then that was the end of chapter 3. Chapter 4, we were doing what do derivatives tell us. So the first thing is that a first derivative can tell you when an original function is increasing or decreasing. Anytime the first derivative is positive, that portion of your function is increasing. Anytime a derivative is negative, that portion of your graph, of your original graph, is decreasing. And critical numbers are all the numbers that make the derivative 0 or undefined, as long as it doesn't make the original undefined. And we want to find them always first because they lead to where the increasing and decreasing could change. They're the only places where that can happen. So our original function is 2/3 x cubed minus 3x squared minus 36x minus 18. So we're always going to do the first derivative and find when is that 0 or undefined. The power rule here is nice because 3 times 2/3, the 3's would cancel. That would be 2x squared. And then minus 6x to the first and minus 36. And the derivative of 18 is nothing. So I've got a quadratic derivative function. It's a polynomial, so it's never undefined. So there's possibly 2 things that make it equal 0. I could divide everything by 2 to make the numbers smaller and easier to factor. X squareds are always easier to factor than 2x squareds. So that helps to divide that 2 out, and then there's a minus 3x and a minus 18. So it's definitely x plus and x minus with a negative in the back. A negative in the back means you get one of each sign. And then you're trying to multiply to 18 and subtract a negative 3. So that means the bigger number is negative. 18 could be 6 times 3. And 3 minus 6 is negative 3. So I have 2 critical numbers, negative 3 and 6. That's part A. They want you to list the critical numbers. There's 2 of them, and separate answers with a comma, it says. Negative 3 and 6. So these are the only 2 times the derivative is 0. It's 2 sections of the original graph that's just flat for a moment. So you're either decreasing and you're flat and you keep decreasing, or you increase, or you're increasing, you're flat, and you either turn around and go down or you keep going up. But at those 2 spots, it's a one moment it's flat. So that gives you a chance to turn around. It's not a guarantee you're going to turn around, but you have a chance to turn around and go the other way. And that not only would be a change in the increasing and decreasing, it also is a special thing we talk about later called a local max or a local min potentially. So this problem is not about the local maxes or mins, but in essence, we're going to kind of do it at the same time. So I put these 2 critical numbers on a number line, and you're going to plug them into the derivative function. You can plug them into the simplified version if you want. X cubed minus x squared minus 3x minus 18. X squared minus 3x minus 18. So I don't want to plug in negative 3 or 6 because I already know those make it 0. I need to plug in something like negative 4 or 0 or 7 would be good choices. So negative 4 squared is 16. Negative 3 times negative 4 is positive 12. Minus 18. This is 28 minus 18. This is 10. But more importantly, it's greater than 0. When a derivative is greater than 0, that's a portion of the graph that's increasing. So we're increasing until we get to negative 3. And then right at negative 3, the graph's flat for a second. So the only question is, does it keep going up or does it turn around and go down? Because the parent function for cubics, it's flat for that moment right at 0, but then it keeps going up. So if you just have x cubed, the parent function of cubics, it doesn't turn around and go back. It's increasing forever, just that one moment in time it's flat. This one's always increasing and it doesn't have a local max or min. Not every cubic does. But some cubics, when you put extra numbers in them like this, when there's extra terms and numbers, then they can bend a little more and they typically will go like this or the other way around, depending if the leading coefficient is positive or negative. So it's just a matter of, does it bend back down again or not? You really can't tell without some experience of what's going to happen here. So now I'm going to plug 0 in, and that's very easy. The answer is literally right there, negative 18. That's less than 0, so it is turning around and decreasing. So then after it was flat for a second, now it's going to keep going down until it gets to 6. Then it'll be flat there. And then since it was increasing first and decreasing second, this is a local maximum, even though they don't care about it in number 15, but we will probably on number 16 answer that too. F prime of 7 is 7 squared is 49. 3 times 7 is 21. But negative 21 and negative 18 is negative 39. 49 minus 39 is also 10. So it is turning around and increasing after that. So this is a local minimum if I was doing that. But all they want here is, when is your graph increasing and decreasing? You're increasing first until you get to negative 3. Don't look at the negative 4 anymore. Then you go down from negative 3 all the way to 6. Don't look at 0 or 7. And then it's 6 to infinity. You go back up again. So there's 2 increasing portions. From negative infinity until the first critical number, which was negative 3, you're increasing. Then you decrease from negative 3 to the next critical number, 6. And then you increase from 6 to infinity again. So in college algebra, they give students the graph. The graph either would be given to them, or maybe they would have got to the point where they know how to graph something like this. College algebra students do this entirely from the graph. They look at the graph. When is it increasing? When is it decreasing? When is it increasing? In calculus, we use the first derivative to tell. We can tell this without graph, and I just sketched a quick graph to show what was going on, but you don't even need a graph to answer this. A positive derivative is increasing, negative derivative is decreasing. Algebra student wouldn't know that. Now, sometimes they use this union symbol. In college algebra, it's common to put this union symbol here that means or. I don't think my math lab can grade that here, so I think they say use a comma. Yeah, it says use a comma to separate answers. So I'm increasing from negative infinity to negative 3, and then comma, also from 6 to infinity. And then I'm decreasing from negative 3 to 6, and this is interval notation. When it looks like a coordinate, but type your answer in interval notation. And it's not that you have to always increase and always decrease in every problem. You could be never decreasing. Like if this was just x cubed, it would be never decreasing, and it would be increasing from negative infinity to infinity. Okay, so again, one time before you take your final on Friday, it definitely helps if you have the time to do the entire review in one sitting. Treat it like a practice test. Give yourself 2 hours because the exam's 2 hours long, and then if you can do all 30 questions in 2 hours, it's a good practice run. If you get a good grade on the review doing that, then you feel pretty confident you're going to do as well or better on the final for that. But at any point, only your highest grade counts. So at any point, once you have a grade you're happy with, or once you know you're going to get a higher grade later, you don't have to do all the problems in any one trial of this. And since I'm breaking this up into 2 days of videos, otherwise it'd be like a 2.5 hour video, I'm going to stop right now, even though I've only answered the first 15. And then it's going to, at best, give me a 50, but that's okay. As long as I get a higher grade later, that's all that matters. So even if, say you do it once and you get a 98 and you made one little mistake, but it's to you, it's not important to redo the whole thing just to try to beat a 98. Some people are perfectionists and they won't be satisfied till they get 100, but others would be happy with an 80 or a 90. If you're happy with the grade, you never have to do it again. But what you could do is then you could go back in and just practice a problem or two. You can just do one problem and submit the thing and grade that one problem. It'll grade it for you, and you can see if you're doing that problem well. Maybe there's a problem you messed it up the first trial and you want to try just that one again. So that's the nice thing, is you can submit this at any point and you'll get a bad grade maybe that time, but it doesn't matter as long as there's a good grade before or after that. So I'm going to submit this, and if we get a 50, then we got everything right. Otherwise, we missed something. And I did get a 50. So everything from 1 through 15's got a green check. 16 through 30 is wrong because I didn't answer them, but that's fine. Tomorrow I'm going to do 16 through 30 and hope to get another 50. And then that would mean that I know all the questions well. But then if I had to get a grade for the review, I would only have a 50 at this point. So then I would need to do it one more time to try to get higher than 50 if I care about that. Okay, so that's it for today. We only have 1 day left of making a video. We'll make a video tomorrow for 16 through 30. And then it'll just be review and final exam is all that'll be left. See you tomorrow.